Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 1931, Paul Dirac published Quantised Singularities in the Electromagnetic Field, a paper that stands as a remarkable testament to his profound insights into the fundamental nature of electromagnetism and its relationship to quantum mechanics. This work, born from Dirac's relentless pursuit of theoretical elegance and mathematical consistency, proposed the existence of magnetic monopoles, hypothetical particles carrying a single magnetic pole, either north or south, unlike ordinary magnets which always possess both. While magnetic monopoles remain elusive to this day, Dirac's paper has had a lasting impact on theoretical physics, inspiring countless investigations into the structure of quantum field theory, topological search for new particles. The intellectual genesis of Dirac's work can be traced to a confluence of ideas emerging from the nascent field of quantum mechanics. His earlier work on the Dirac equation, published in 1928, provided a relativistic description of the electron, predicting the existence of antimatter, a prediction soon experimentally confirmed with the discovery of the positron. This triumph instilled in Dirac a deep conviction in the power of mathematical theory to unveil previously unknown aspects of the physical world. Concurrently, developments in the understanding of electromagnetism, particularly its formulation in terms of vector potentials, began to reveal subtle topological features. These potentials, while not directly observable, play a crucial role in describing the electromagnetic field in quantum mechanics, and Dirac's attention was drawn to the implications of these potentials existing even in regions where the magnetic field is zero. Aronov and Bohm would later elaborate on these implications, showing that the potentials themselves have physical consequences. Dirac's paper begins by considering a familiar classical description of electromagnetism in terms of electric and magnetic fields. However, he quickly shifts focus to the vector potential, denoted by the letter A, which relates to the magnetic field through a curl operation. In standard electromagnetism, the magnetic field is divergence-free, meaning it has no sources or sinks. This reflects the empirical observation that magnetic monopoles appear to be absent from our universe. Dirac, with characteristic boldness, questioned this assumption. He explored the consequences of allowing for point-like singularities in the magnetic field, corresponding to the presence of isolated magnetic charges. To accommodate these hypothetical monopoles, Dirac introduced a mathematical artifice, a string extending from the monopole to infinity, along which the vector potential becomes singular. This string, while mathematically necessary to describe the monopole, presented a physical puzzle. Its presence seemed to violate the principle of locality, a cornerstone of physics. The location of the string appeared to be arbitrary, yet its existence seemed to influence the behavior of charged particles. Dirac resolved this paradox with a stroke of genius. Invoking quantum mechanics, he recognized that the wave function of an electrically charged particle interacting with the electromagnetic field must be single-valued. This seemingly innocuous condition imposed a profound constraint on the allowed values of the magnetic charge, denoted by the letter G. Specifically, Dirac showed that the product of the electric charge, denoted by the letter E, and the magnetic charge must be an integer multiple of a fundamental constant, Planck's reduced constant, denoted by hbar, divided by 2. Mathematically, this relationship may write as E times G equals N times hbar divided by 2, where N is an integer. This is known as the Dirac quantization condition. This condition implied that if even a single magnetic monopole existed in the universe, all electric charges would necessarily be quantized, taking values that are integer multiples of a fundamental unit. Electric charge quantization was already an observed fact, but its explanation remained enigmatic. Dirac's monopole theory offered a compelling theoretical explanation for this phenomenon, linking it to the possible existence of magnetic monopoles. It suggested a beautiful symmetry between electricity and magnetism, a symmetry that is not apparent in our everyday experience. The immediate impact of Dirac's paper was significant. Although perhaps more intellectual than directly experimental, it provided a theoretical framework for contemplating the existence of magnetic monopoles, stimulating numerous searches for these elusive particles. The quantization condition became a guiding principle in these searches, dictating the expected strength of the magnetic charge. Furthermore, Dirac's work sparked intense interest in the topological aspects of electromagnetism and quantum field theory. The concept of a Dirac string, despite its initial strangeness, became a prototype for more sophisticated topological defects in field theories, such as vortices and domain walls. The later use and evolution of Dirac's monopole theory have been far-reaching. In the 1970s, Gerard T. Hooft and Alexander Polyak have independently demonstrated that magnetic monopoles arise naturally as solutions to certain non-abelian gauge theories, which form the basis of the standard model of particle physics. These T. Hooft-Polyakov monopoles are topologically stable, meaning that they cannot decay into ordinary particles. Their existence is a consequence of the underlying mathematical structure of the gauge theory. These discoveries greatly strengthened the theoretical case for the existence of magnetic monopoles. Though experimental detection has remained elusive, Dirac's ideas also profoundly influenced the development of modern condensed matter physics. In particular, the concept of Berry phase, a geometric phase acquired by a quantum system as it evolves adiabatically, is closely related to the topological ideas introduced by Dirac. The Berry phase has important consequences for the behavior of electrons in solids, leading to phenomena such as the quantum Hall effect and topological insulators. These materials exhibit novel electronic properties that are protected by their topological structure, making them promising candidates for future electronic devices. The reception of Dirac's monopole theory was initially mixed. Some physicists were skeptical of the idea of magnetic monopoles, viewing them as purely speculative entities with no experimental basis. Others were intrigued by the theoretical elegance of Dirac's argument and the potential implications for understanding charge quantization. A key sticking point was the aforementioned Dirac string. The non-locality appeared problematic. Julian Schwinger was one of the most notable critics. He argued that Dirac's theory was intrinsically flawed due to its reliance on singular potentials and the arbitrary nature of the string. Schwinger developed an alternative theory of magnetic monopoles based on source theory. He tried to avoid the need for singular potentials. Despite these criticisms, Dirac's paper continued to exert a powerful influence on theoretical physics. Over time, physicists developed a deeper appreciation for the topological aspects of Dirac's theory and the importance of gauge invariance in quantum field theory. The development of T. Hooft-Polyakov monopoles provided a concrete realization of Dirac's ideas within the framework of modern particle physics, addressing some of the earlier concerns about the physical reality of magnetic monopoles. Dirac drew inspiration from a variety of sources. Einstein's theory of general relativity, with its emphasis on geometrical concepts and coordinate invariance, undoubtedly influenced Dirac's thinking about the role of the vector potential in electromagnetism. He looked to reformulate electromagnetism to incorporate quantum mechanics. The work of Hermann Weyl on gauge theory, which sought to unify electromagnetism and gravity, also played a role in shaping Dirac's side. The impact of Dirac's monopole theory on subsequent work has been immense. T. Hooft and Polyakov's discovery of monopoles in non-abelian gauge theories, already mentioned, is a prime example. The work of Michael Berry on Berry phase and its applications in condensed matter physics can also be traced back to Dirac's ideas. Furthermore, Dirac's paper has inspired countless theoretical investigations into the properties of magnetic monopoles, their possible role in cosmology, and their potential for experimental detection. In conclusion, Paul Dirac's 1931 paper, Quantised Singularities in the Electromagnetic Field, stands as a shining example of theoretical physics at its finest. Although magnetic monopoles remain elusive, Dirac's work has profoundly shaped our understanding of electromagnetism, quantum mechanics, and the topological structure of the universe. His insistence on mathematical consistency and theoretical elegance led to a prediction that continues to inspire and challenge physicists to this day. Whether magnetic monopoles are eventually discovered or not, Dirac's legacy as one of the greatest theoretical physicists of the 20th century is secure. His paper serves as a reminder that the pursuit of fundamental knowledge often requires venturing into uncharted territory, guided only by the light of reason and the beauty of mathematical truth.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.